Okay, greetings everyone. Welcome in to my channel. I am Professor L, and this is a live stream for math tutoring. So it's a Friday night, and no time like a Friday night to hang out and do some math. So yeah, that's what I'm going to be doing. And yeah, so I'm just offering up this space in this time frame for math tutoring and supporting students. So if you are out there and you need help with math, yeah, it's open to the public that you can post a problem in the chat and I will do my very best to work it out. What I've decided to talk about tonight and present is transformations of the graph of the squaring function. And so it is a second degree polynomial, and it's also the name of the graph, or the shape of the graph rather, is called a parabola. And yeah, and so I'm going to be showing transformations and sketching the graph of and transforming the graph using those different transformations and talking about. So you have the squaring function, and what it does is it takes and it calculates the area of squares. So what you're doing is you're inserting a side length into the domain, and then that function is returning the area of a square, essentially. So it all relates back to geometry in some form or fashion. So yeah, we're going to move on from systems for now. We might have to revisit them in the near future. And we're going to go back to just a second degree polynomial. And what I want to do is spend the next couple of days probably discussing all the conic sections. I've been reading up on, doing a little bit of reading on the hyperbolas and the ellipses. So I'm hoping by this weekend I'll be more comfortable in trying to sketch the graph of some of those funky looking functions. All right, so here we go. Transforming the graph of the square function. And I wish that I would have remembered to do it before. I got to dig out another marker, so I apologize. And that heading was not centered, so oh my goodness, did I get a dry one? Tragic. All right. I hope that's the only dry one. Sometimes the lids don't go on correctly. All right, that looks a little bit better. All right, so there we go. So now I have to remember next time to try to center that heading a little bit better. So we have this. We have the graph y equals x squared. And I'm going to go ahead and get out my Cartesian coordinate system. And we're going to discuss all of the different types of transformations. And I'm going to introduce the transformations using the squaring function, but transformations apply to all of the functions. And really, I'm using the word improperly because the squaring function, well, I guess it is a function. So it does pass that initial vertical line test, but it fails the horizontal line test. So yeah, I guess I'm saying it correctly then, because it would pass that, and we'll look at that here in a minute. But what we're going to do is we're going to go ahead and start by plotting the graph of this function using a table, x comma y, and negative 1, 0, and 1. We're just going to use those happy 3 points. So when I plug in when x is negative 1, when you square a negative, you get a positive. So when I plug in 0, you square 0, you get 0. And then when you square 1, you get the same, a positive. So it leads to this type of graph. Negative 1, positive 1. And that is way off. X comma y. And then, so we'll plot these points. You've got negative 1, 1, that point, 0, 0, and you've got positive 1, 1. So we've got this type of thing going on. So this is the basic graph of the square function, and I just want to fix that one right there because it literally it doesn't go negative unless you perform a transformation on it. So we have that basic graph of y equals x squared. So we'll first transform the vertical. We'll talk about the vertical stretch. Not the stretch, just the vertical shift first. And vertical shift, vertical orientation is perpendicular to the earth. So if you're like we're standing in a vertical, if you're standing, you're in a vertical orientation. When you're lying down, you're in a horizontal orientation. So if I were going to shift this graph vertically and transform it vertically, then I would use a vertical shift. And it's known as, it's y equals x squared plus k, where this k value is shifting the graph up or down. So you're going up or down k units. So if I were wanting to make a new equation, y equals x squared plus 4. We'll just go 2. Then I have this very same graph right here. Only now it's got this thing going on. It's the very same graph, only it's been shifted up 2. So what this is doing, it's not affecting the x values. What it's doing is it's affecting the y values. So if you notice, when you build a table of values to plot, this function, and you use those same 3 points, -1, 0, and 1, and you plug in, you're going to get, all you're doing is you're adding 2 to the values of y. So if, we'll just do the first one, -1 squared plus 2 is 1 plus 2, which is 3. And y equal 0 squared plus 2 is 0 plus 2, which is 2. And y equal 1 y squared plus 2 is also 3. So we're just shifting that graph up. So we've got -1, 3 is on there. We'll move it up a little bit, and we'll not shift it any higher. We'll say 3 is about right there. So 0, 0 is not on there. It's 0, 2 now. And then 1, 3 is also on there. So we've got the vertical shift. And so what it's doing is it's affecting the k. There's a k constant, and it's at the end of the equation. And so then you have a horizontal. You also have the horizontal shift. And the horizontal shift is x minus h, where h shifts, well, 8 units. Hang on. H moves left and right. So, and this has to do with those 0 values. If you find the 0, then it's a factor. So the negative shifts it to the left, and the positive value shifts it, or sorry, positive moves it to the left, and negative moves it to the right, which is backwards. It's not intuitive. So we'll say positive left and negative right. I guess that's a little bit clearer to say. So if I were going to take this function and perform a horizontal shift, here, we'll do this as an example. We'll have an example right here, and we'll say y equals, and where that transformation is appearing in the graph now is inside of the square. Inside, it's attached directly to x inside the square. So you'll say x minus, and then we'll just say 2 quantity squared. So x minus 2, you would actually shift it to positive units. So you would be here. So it's the same graph going over to positive. And so what this is doing, this horizontal shift is only affecting your domain now. So if I were going to sketch a table of this graph, here we can do it here because we're not going to shift it to the left, x comma y here. And we'll, let's see. Well, we're going to pick those same 3 points. -1, 0, and positive 1. And we'll evaluate and plug in. So we'll have y equals, let's see, at negative 1. Minus 2 squared. That's negative 3 squared. It's not going to be on my graph. Mine is not on my graph. Negative 1, 9 is all the way up there. And then let's see where 0 ends up. Y equals 0 minus 2 squared. That is negative 2 squared. And that is 4. So we got 0, comma 4. And then let's do, well, we know that the graph shifted this direction too. So this is my new point. So 1, let's see what 1 is. Y equals 1 minus 2 quantity squared. That's, oh, well, okay, negative, so 1 minus 2 is negative 1 squared. And that put me at positive 1. So we have 1 comma 1 is on there. So it's this graph here. And then I bet if we extended this one out a little bit, I bet that 3 comma 1 would also be on there. So we'll do that. So let me see here. We would have to find 2 comma 0 and then 3 y equals 3 minus 2 quantity squared. So that's going to give me 1 squared, which is 1. So 3 comma 1. So here is, we don't want to have sketch that point. The graph of just shifting it. Again, to the right 2 units. So we've got the vertical and the horizontal shift taken care of. We have the stretch. Let's see, what other transformations are there? There is a stretch and a reflection. So if let's go ahead and erase all of this. And again, this is just me practicing, playing around with these concepts and trying to gain more skills. Working with the math and trying to explain math. So we'll go ahead and raise, we'll leave the horizontal shift up for a moment. So we have the negative reflection. So we have an x-axis. We have an x-axis reflection at y equals negative x squared. My negative is kind of crooked. Let me fix it. So, for example, on the table, let's see, if we're going to, let's see, x comma y, and we want to just reflect the basic graph, then we'll go negative 1, 0, 1. And then we're going to plug in negative 1 squared. And that's going to give me, let's see. So negative 1 squared is positive, and then it's negative. So that's negative 1. And then y equals 0. It's negative 0 squared is just 0. So that's on there. And then also with positive 1, negative 1 squared is just negative 1. So we have these points on there as well. So what this graph is doing, that negative is causing it to have a flip where now where it's concave up here, where it's point you have a minimum value, the vertex. Well, when you have a negative graph, you have a maximum at the vertex. And so the graph here goes from a decreasing function to an increasing function. Well, when you have a negative graph of reflection, you go increasing and then you end up decreasing. So over here, when x is positive, you're actually decreasing on this type of graph, that transformation. And this is the one that we need for modeling projectile motion and falling bodies. We need this x-axis reflection right here for that equation. So that's one of the reasons why I wanted to do these transformations actually, is because of that x-axis reflection. All right, so the only other major transformation for these graphs that we need is that the vertical stretch. So we had horizontal and vertical shifts, but what we also have is horizontal and vertical stretches. And so we'll put that on here for the vertical stretch. And what that is it's an A value. And we'll put all these transformations together here in just a minute. And I'll make a pretty graph with all of them. We'll just make up a function. But you have this A value, and if A is greater than, if it's greater than 1, I think. We'll say the absolute value of A is greater than 1. That'll be more correct. Then you have a stretch. And if A is, the absolute value of A is between 0 and 1. Okay, if the absolute value of A is between 0 and 1, you have a compression. Or shrinking. And so basically an example of that would be like if we had something like, I won't build the table, but y equals 2x squared. X, comma y. And you pick those same 3 values here, -1, 0, and +1. And then you plug in, you're getting 2 times -1 squared, which is -1 squared is 1, 2 times 1 is 2. And then you've got this one for 0, it's just 0. And then +1, you've also got +2. So by a factor of 2, you've got -1, 2 here now. And you've got 0, 0, and 1, 2. Where it's just where it's just stretching that graph out just a little bit. So you can kind of see the comparison from the normal graph here to your stretch graph. And then let's see one more. Let's do for y equals 1/2 x squared, where your a value is a shrinking, and do a table real quick, and then we'll be finished with all of them. We'll put them all together and see what that looks like. X comma y, -1, 0, and 1. And when you plug in -1 here for 1/2, that's 1/2, and then 0, and then 1/2. So at -1, you're at 1/2 now. Got this one. Okay. All right. So that is a basic theory behind how you transform basically any function. So I want to try to use transformations in the trig functions eventually, because I do want to make it back to trig. But we needed to revisit algebra, and I needed to tighten up my algebra a little bit. So hopefully I'll make it back to trig soon. But for now, we're having fun with these polynomials. So at least I am anyway. All right, so let's go ahead and yeah, so I'm going to go ahead and erase almost everything. And I'm just going to make up a function off the top of my head, which is kind of dangerous because I historically am not creative in coming up with last minute functions. Let's see if I have one. I did ask AI earlier, but I didn't actually look at them, so I don't know. I want to put all of them together. So I'm going to get ahead of myself here. I really feel like we need to put all these transformations together. And I know that I've played around with changing forms in some of my previous videos, where I went from standard form, where it's like a polynomial form, and I turned it into vertex form using the completing the square method. And that's fun. I enjoy doing that kind of stuff. But tonight it's about transforming the graph and looking at those different types of transformations and how it affects the graph and how it affects how the equation looks. So we have this y equals a times x minus h y squared plus k, where a is your vertical stretch, H is the horizontal shift. And K is your vertical shift. So example would be y equals 1/2 times x minus 2 quantity squared plus 2. So I am just, and we'll change that. We'll go ahead and put 2 in there. So I'm just using those, using all the transformations, those same functions that we used before. And then we're going to make a table of values, and I'm going to just find, so we have our basic function y equals x squared, and I'm shifting it to the right 2 units, up 2 units, and then I'm having a factor of 2 by 2. So we have the vertex, because this is actual vertex form. So I'll put that in here, vertex form. At h comma k. So your vertex, hang on, let me. So I want to figure out my vertex before I figure out where my domain is going to be. So vertex is at positive 2, positive 2. So I need to pick values in my domain. We can still do -1, 0, 1, but we also have to do some more points in here. 1, 2, 3. All right, so let's go ahead and do this. So y equals at -1, we've got 2 times -1 minus 2, quantity squared plus 2. And that's going to be -3 squared plus 2. So remember order of operations, we got to square it first. That is a really big value. All right, we're 18 plus 2. We're at positive 20 at -1. So we might not start at, we're not going to start at 20. How is that possible? Okay, well, I gotta believe it. All right, so we'll go to 0. Y equals 0, 2 times 0 minus 2 squared plus 2. So that's -2 quantity squared plus 2. Just 2 times 4 plus 2. That factor of 2 is really making a lot. It's really stretching a lot because I'm still at 10 at 0. And I don't know if I want to make my Cartesian coordinate system have that big of a scale. That is not a straight line. Oh well, we're just going to go with it. It's Friday. We'll be a little rebellious there. Make your lines curvy, I guess. I don't know. Okay. So y equals, what about positive 1? So we got 2 times 1 minus 2 squared plus 2. So that's 2 times 1 minus 2 is minus 1, corner square plus 2. So we've got 2 times 1 plus 2 is 4. All right, finally, a value I can live with here. And then we know that, let's see, 2 comma 0, that's my axis of symmetry. Because my vertex is at 2 comma 2, I know that's on there, so I can get that one. Y equals 2 times 3 minus 2 corny squared plus 2. That is 1 squared plus 2. Plus 2 is 4 again. Okay. So it's going to be symmetrical about the axis of symmetry. So since that's at 2, then we're going to do, it's going to be symmetrical about that line. So and we have 1, 2, 3. And we're not going to calculate anything past, because at -1 we're way up there, and our y-intercept is at 10. So we don't even have the y-intercept yet, so that's not even on there. So we're not going to start that until 1 comma 4. And then we have 2 comma 2. And then we've got 3 comma 4. And then I would really like to see, instead of 0, let's go back and calculate 1/2. And I can put that up here. I'm going to get a little carried away and realize I've been talking already for 40 minutes. Okay, so let's go ahead and calculate 1/2. Y equals 2 times 1/2 minus 2 squared plus 2. And let's see, 1/2 minus 2 is -3/2. So we'll have to just subtract the fractions just to make sure, but I'm pretty sure. 2, 1. So 2 goes into 1, 2 times 2 times 2 is 4. So that's -3/2. Okay. Anyway, me not being lazy, showing the math. Plus 2. Because it's Friday. I'm exhausted. Takes a little bit of discipline sometimes to come and hang out and do math on my board, especially when I'm tired. But it's good for me, and I need to have a routine about it. So when, let's see, -3/2 squared, we know it's going to be positive, so we're just going to focus on squaring the fraction. So 3 squared is 9, and 2 squared is 4. and then that becomes 2 times 9 is 18/4, and then 8/4 is 2, so 18 plus 8 is 26/4, which is, let's see, 24, 6, 26. So it's like 5, 6, 7, almost 7. So it's between 6 and 7. 26 divided by 4. Okay, 6.5. So at 1/2, we're at like right in here. So that point's on there. I just want to see what that next point would be. Yeah, so the vertical stretch really does affect the graph quite a bit. And so I just wanted to kind of pull it together with all of the transformations. And then I guess we'll just, so that the graph is symmetrical, we'll come out here and we'll calculate that other value at 1/2. We get the same value because it's symmetrical. But if we do see, it wouldn't be 3.5. Let's see, 1/2 would be, yeah, 3.5. So 3. Yeah, 7/2. And at 7/2, you should still get 26/4. You'll get 26/4. And we can verify that real quick just for fun. So y equals 2 times 7/2 minus 2, quantity squared plus 2. So let's see, 7/2 minus 2. So just get an improper fraction, 4/2, and then that's going to be positive 3/2. And then two times 9/4 plus 2. That is 18/4 plus 2. So I'll just say that that's 8/4, and then you get 26/4. So we have there we go. Okay, very good. Yeah, so I am not gonna have any problem with going ahead and stopping there and calling that a win. I was probably too tired to do this tonight, but I'm glad that I made it. And it's the other side of success, I guess. Well, yeah, so I am going to go ahead and end the stream since I don't have any students and I don't have any math problems to work for students. And yeah, and I have the weekend. And then just a reminder that I will be back on Monday between 6 and 7 p.m. Central Time. And if you are watching, thank you so much. I really appreciate it. And if yeah, if you have time during between 6 and 7 p.m., and you want to drop by to spend a couple minutes to do some math, you don't have to stick around for the whole hour. But also, if you do post a problem in one of the comments, I will get the notification and go back and look at it and maybe have it prepared for the next day or something like that. But again, yeah, this is just fun. And so, just I hope that everyone has a wonderful rest of their Friday evening. And yeah, I look forward to seeing you next time. Bye.